Hi and welcome to my presentation on the exploitation of browsers. This study advised by Professor Jonathan Weissman, who explored the V8 JavaScript engine from Google. So, first of all, the study started as a way to explore an increasingly popular attack surface, web browser. Nowadays, many applications have the web-based versions, and even binary analysis frameworks like Binary Ninja have a cloud version. The JavaScript engine is a crucial part of the browser, and on its own, the engine is already a really complex piece of software. A simple case study is presented to demonstrate how an attacker can gain arbitrary code execution on the host system running the web browser. So, first of all, let's break down a typical browser exploit. It usually starts with an initial memory corruption bug, for example, a restricted out about memory access or use after fully. From there, an attacker is able to build exploit primitives such as address of and fake object, which we will discuss in a few moments. By using the exploit primitives, the attacker can gain arbitrary memory read and write, and eventually write and execute shellcode on the system. In the case study, a vulnerable functionality is introduced to the engine that allows accessing elements of an array at arbitrary indices. Let's say that we have an out-of-bound array here that we can access memory outside its boundaries, and we can read from and write to the data of other objects in the heap, where most of the JavaScript objects are allocated. The address of primitive allows an attacker to read the address of any object. This would be normal in programming languages like C, but it is unusual in JavaScript because the memory allocation are all handled by the engine, and addresses of objects are not visible to the JavaScript code itself. When we reverse this primitive, we get the fake object primitive, which allows us to put data that resembles an object in memory and just tell the engine that there's an object at this address. For example, the map value of an object typically marks the start of an object. This value is not visible to the JavaScript code itself, just like memory addresses, and here we put data that resembles an array buffer object as elements of a number array. And if we tell the engine that there's an object starting from this address, the engine will interpret that this is an actual data of an array buffer, and we get back an array buffer object that we entirely control its data, its properties. And after obtaining the array buffer object, the backing sort pointer of this object, which points to anywhere we want to read and write data, is controlled by us. And a typical technique is to generate WebAssembly code that will get compiled in memory and appear at the read-write execute memory region. We will utilize the exploit primitives to find the address of this region and write our shellcode to it. Since this memory region is both writable and executable at the same time, this shellcode will replace the originally compiled WebAssembly code, and when the WebAssembly function is called, our shellcode is executed. And so, as a result of our shellcode executed, when visiting the malicious HTML page that contains a JavaScript exploit, the calculator program pops up to demonstrate that our shellcode is executed. And through the study, a key lesson to take away is that always browsing the web with caution. Due to the increasing popularity of web applications, web browsers have been a more attractive attack surface than ever. And so, thank you for joining my presentation, and please let me know if you have any question. And thank you, Professor Weissman, for your guidance during the study.